Yeah, shut up now. Okay. This is the last thing I'm going to do before we go on to the next topic. So let's just do sort of a combination example. Oh, by the way, so last time I got sort of confused on that. It turns out all the math was right in that what I did last time, but I sort of got confused on how to like interpret it, make sense out of it. But I don't know if you notice on D2L, I put up a little bit clearer description of how to relate the answers you got using a circular cross-section calculation to the answers you get using a thin-walled calculation. Okay, so now let's say we have a beam like this. And there's a 5,000 Newton force to the right on this side. And the length of this beam is 1 meter. And at the midpoint, you have a downward force of 4,000 newtons and a torque in this direction of 2,000 Newton meters. And we're going to calculate a stress halfway between the midpoint and this end. And if you look at the cross section, it's a rectangular cross section. The width is 2 centimeters, 0.02. The height is 5 centimeters. And the thickness is the same everywhere. So let's say that thickness is 3 millimeters. And if this is the neutral axis, let's say we want to calculate the stress at this point A, halfway between the neutral axis and the top. So I'll call that point A to help you with your bearings on this. That's the y-axis. This is the z-axis. And the mass, I said this has a mass of 50 kilograms. I guess I'll leave it like that, but it actually wouldn't be very hard to figure out a realistic mass. My guess is that's way too big a mass for the dimensions that I have here. If you calculated the volume of this beam and used the density of steel or something, you could see whether you'd get anywhere close to 50 kilograms. I would guess it would be quite a bit less, but let's say, because that's what I have in my notes, 50 kilograms. And we want to calculate the stress tensor at A. And the principal stress tensor at A, and then the maximum shear stress at A. Okay, so the first thing we have to do is we know that the stress tensor at A is going to be the stress tensor due to tension compression plus the stress tensor due to bending moment plus the stress tensor due to shear force plus the stress tensor due to the torque. And so let's start by calculating the internal loads at that point. Notice usually when we calculate internal loads, we calculate them as a function of x. But since we're given a location, an x value where we want to calculate these, we might as well just make the one finite cut and just calculate those without any functions. And once we figure out which of those are non-zero, we'll think about whether we have techniques that are going to work for the internal loads that we have. Because remember, there's pretty strict restrictions on on what the cross-section dimensions can be and stuff like that. And then we'll go from there. Okay, so we'll do the cut. We have the 4,000 Newton force. A torque of 2,000 Newton meters. 5,000 Newton force here. And then we have a weight force. Now that we've chosen the cut we want to make, we can represent the weight force as a point force. So if the total mass of the whole beam is 50 kilograms, the mass of this piece, the mass of the cut isolating is, we're dealing with 3/4 of the length of this thing. So 3/4 times 50, so 37.5 kilograms. And what's that times 9.81? Nope, that's good. Yeah, I mean, if I don't say it, then it always is what it looks like. On a test, I always say it. In the homework, sometimes often I don't. That's what I always mean, is for it to be halfway. Yes, that's right. Okay, so, and then we have the internal loads: tension, shear force, bending moment, and torque. And this distance, what's the distance from the left end to where the weight's applied? That's half of this whole, the length of this whole thing is, our cut is 0.75 meters. So this is 0.375. And this distance is 0.5. And the whole thing is 0.75. So Newton's second law says 5,000 0 plus 0 negative 367.9 plus 0 negative 4,000 plus T negative V is equal to zeros. So T is negative 5,000. So it's in compression with a force of 5,000. And shear force is negative 4,367.9. And we'll do the moment equation about the x-axis. We have a torque of negative 2,000 plus the internal torque is equal to 0. And so the internal torque is positive 2,000. And then the moment equation about the z-axis, about point is at the left. You could put it anywhere. So we have 367.9 times 0.375, and that's a clockwise moment, so negative. So negative, what's the number? What is it? 0.375 times 367.9 is the total moment. One, 9, 6. Okay. And then we have the downward 4,000 Newton force. The magnitude is 4,000 times 0.5. That's also clockwise, so negative, so minus 2,000. And then we have plus m minus v times its moment arm, and this time that's usually minus vx, but now we know x is 0.75. So I'll do that as 0.75 v. Is equal to 0. So m is equal to 2137.96 plus 0.75 times times 0.75 times negative 4367.9. What do you get for that? $3279.93. Okay. And so what do you get for a total number? Negative 1, 1. 3. Okay, go with that. All right, so we have non-zero values for all of these internal loads. So we have non-zero tension, bending moment, shear force, and torque. So we need to make sure that our cross section and our loading applies for each one of these. So what are the requirements for tension compression? I didn't really give you any of those. Bending moment. So that one has to be prismatic, straight. Yep. And we're good with all those. shear force, what are the requirements there? Yep, either rectangular or circular at the neutral axis. This one is rectangular, so that works. And then the last one is the torque. What are the requirements there? Yep. Or thin-walled. This is thin-walled, so we're good with all those. So we can do this calculation. Yep. No, then you can't do the problem at all. I mean, you could calculate sort of like components. You could calculate, you know, if you're not good with the shear force, but you're good with M, and you're also good with the tension or compression, you could calculate the normal stresses, but it's basically like all or nothing. You can either do this problem, or if you can't do the whole problem, usually there's not much useful that you can get out of doing part of the problem. Yes, yes, that's a good question. So, so if, like, for example, what if we didn't have the requirements for, like, say, what if this wasn't symmetric about the y-axis? Okay, then we wouldn't be allowed to use this to calculate the stresses due to bending moments. But what if our the point we were interested in happened to be on the neutral axis? Well, then the bending moment isn't gonna, the neutral axis is where there's no stress due to bending moment anyways. So you'd still be able to do this in that case. Same thing with shear. If it doesn't meet the shear requirement, but you're at the top or the bottom, you can still do it because the stress due to the shear force would be 0. Okay. So first, calculate the stress due to tension. So it's an x stress that's equal to the tension over the cross-sectional area. And the cross-sectional area is, so we can do it as the outer area minus the inner area. The outer is 0.02 times 0.05. The inner, the wall thickness is 3 millimeters. And so you're removing that wall thickness from both sides. Okay, so the length of this inner width is 0.02 minus 2 times 3 millimeters. So that's going to be 0.014. Right, you're removing 6 millimeters from it. Any questions about that? Yeah. So we're trying to come up with the length of this inner dimension here. So the way we're going to get that is it's going to be the outer dimension minus the thickness of this wall minus the thickness of this wall. Okay, so it's not just subtracting 3 millimeters, it's twice that. Okay, so we have to subtract 6 millimeters. So this is going to be 0.014 times 0.044. And you get an area of, yep, so 3.84 times 10 to the minus 4 meters squared. Okay, well, while we're at this, maybe uh, I'll erase this in a second, but that means that the volume of this shape, since it has a length of 1 meter, the volume is this meters cubed, right? Because we're just multiplying this area by 1 meter. So 3.84 times 10 to the minus 4 meters cubed. And if the mass is 50 kilograms, let's figure out what the density is. So 50, the density is 50 divided by 3.84 times 10 to the minus 4. What do you get for that? Times 10 to the 5th kilograms per meters cubed. Anyone have an idea of what the density of like steel is? Steel is 7,000 kilograms per meters cubed. So this isn't a very realistic density. I don't know. It might be made out of, it's made out of black hole or something. Yeah. Yeah. It's made out of black star. Beams like that are expensive. Yeah. And like you're trying to leave and it's sucking you back in. Okay. So sigma xx is what we got for the tension, negative 5,000 divided by 3.84 times 10 to the minus 4. What do you get for that? Okay, so our stress tensor due to tension compression is negative 1.302 times 10 to the 7, zeros everywhere else. Yeah, I mean, as long as you can make sense out of it to yourself, that's fine. And now the stress due to the bending moment, that's going to be equal to negative my over I. I is 1/12 times, so the way we're going to do this is calculate I for the outer rectangle and subtract I for the inner rectangle. They both have the same neutral axis, so we don't have to use parallel axis theorem or anything like that. So 1/12 times the base times the height cubed minus 1/12 times the base of the inner rectangle, 0.014, times 0.044 cubed. And if you calculate that, you get 1.090 times 10 to the minus 7 meters to the 4th. And so sigma xx is negative of what we got for the bending moment. Times y. Y is the distance from the neutral axis to the point we care about. this whole distance from the neutral axis to the top is 0.025. So this is 0.0125. And then divided by 1.090 times 10 to the minus 7. And what do you get for this? 1.305 times 10 to the 8. Ooh, this beam is probably in trouble, by the way. These are pretty big stresses. My neutron star! It broke. Okay, so the stress tensor due to the bending moment is 1.305 times 10 to the 8, 0, 0, 0, 0, 0. One thing, though, at the point that we happen to be interested in, I mean, if that point was special for some reason, I mean, I just chose to do this point so we didn't have to calculate everything as functions of x and y and stuff. But if there really was a reason that this point was especially important, we do get a cancellation here of a little bit of the stress, the compressive stress that's coming from the internal compression and the tensile stress that's coming from the bending moment. So they will offset a little bit. And now the shear stress, the shear force. So this is going to be, we're going to have to use that temporary capital coordinate system. And the shear stress is negative V times Q divided by I times B. That is, so that always has the z-axis pointing out of the wall. So in this case, that would be like rotated this way with your capital Z-axis like this, your capital Y-axis like this. And then we'll have to use a rotation matrix to represent it in the coordinate system we want. No, don't worry about where the origin is. So first let's figure out Q. Okay, Q is going to be a little bit of a pain on this. So what we have is, so here's our shape. Here's the neutral axis. Our line of interest is here, and so this is the area. So we're going to have to figure out the centroid of that area and then calculate the distance from the neutral axis to the centroid of that area. The centroid is going to be up here somewhere. And then our D is going to be this distance. The area isn't too hard to calculate. I guess the way I did it was I calculated the area of the big rectangle and subtracted out the small rectangle. So you can do that in 2 steps instead of 3 steps of breaking it up. Um, so this Q is going to be equal to A times D. A dot 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 is equal to 1.17 times 10 to the minus 4. And for the centroid, I did it the same way. So the y centroid is equal to 1 over the total area times the area of the big outer rectangle, which would be 2.5 times 10 to the minus 4 times the y centroid of the big outer rectangle, which is 0.01875. And then subtract the area of that removed rectangle, 1.33 times 10 to the minus 4 times the centroid of the removed rectangle, which is 0.01725. And you get a value of 0.205. Okay, so Q is equal to 1.17 times 10 to the minus 4 times that should have been 0.0205. And so Q is equal to 2.393 times 10 to the minus 6 meters cubed. The last thing we have to figure out, we already have I, now we have Q. B going to be? You have a feel for what that B is doing in there? So what that B is doing is telling you how much material you have, keeping this thing from breaking apart at that point, from shearing apart at that point. And so it's not just the thickness of that wall that's keeping it from happening. It's the thickness of this plus the thickness of that. Okay. Well, no. So like it's not going to be this 0.02. It's going to be 6 millimeters. You know what I mean? Oh, I see. Oh, the whole thickness. Right. That's right. So B is 0.003 plus 0.003. You have to take both of those two into account. So, okay. Yeah, right. Because that's in there because it's taking into account how much material there is resisting this loading. Yeah, right. At this height. Remember, the shear force only refers to a certain height. It doesn't refer to like a certain point. It doesn't differentiate between the point here and the point here. Okay. So think of it as we're actually calculating it along a line. Yep. Yeah. 0.02. Yep, exactly. And so, right. And so that B gets a lot bigger. Well, also the Q gets a lot smaller. And so the shear stress you'd have along that top line is really, really small compared to what we're going to see. Okay, so finally, yeah, yes. Yes. Well, yes, that's right. Because our origin is the neutral axis. And so our shear stress, you know what? We're not doing this. This is for torque. This is still going to give us uh, the stress due to shear force is still just going to give us the actual the stress in our coordinate system. It's the torque where we have to worry about like rotating the coordinate system. So this is just going to be that. This is going to be just lowercase x, y. Um, and so the V we're using is negative 4367.9. Um, the formula has the negative, so we have a second negative. Q is 2.393 times 10 to the minus 6. I we calculated above 1.090 times 10 to the minus 7. And then B is 0.006. And you get 1.599 times 10 to the 7th. So the stress tensor due to the shear force is 0, 1.599 times 10 to the 7, 0. Then 1.599 times 10 to the 7, 0, 0, zeros. And then the last one is the torque. This is a thin-walled cross-section. So we're using the formula that says the capital XY shear stress is equal to negative torque divided by 2 times the thickness of the wall times the area at the median of the wall. To calculate the area of the median, in this case, because of the, I don't know, is that just going to be the average of the inner and outer area in this case? It sort of seems like it should be, but yeah, because yeah. Well, you get, so the area at the median is going to be 0.05 minus 3 millimeters. That's subtracting half of the thickness on the top and half of the thickness on the bottom, times 0.02 minus 0.003. And the area is 7.99 times 10 to the minus 4 meters squared. What's the thickness at the point we're looking at? 0.003. It's just the wall thickness at the point where we're looking. Yeah, remember for thin-walled, for calculating the stress due to torque in thin-walled cross sections, there's we can't distinguish between across the wall, you know. Just the wall has a single value, and because it's thin, that value doesn't change very much. And so this is just going to be 0.003. Yep, yep, that's right. Yep. And so in the capital coordinate system, the temporary coordinate system, where's our torque? Our torque is positive 2,000. So this is negative 2,000 divided by 2 times 0.003 times 7.99 times 10 to the minus fourth. And you get negative 4.172 times 10 to the eighth pascals. So in our capital coordinate system, we have 0, negative 4.172 times 10 to the eighth, 0, then negative 4.172 times 10 to the eighth, 0, 0, zeros here. And now we have to re-express this in our coordinate system. So we're going from a coordinate system oriented like this to a coordinate system oriented like this. Nope, it's not right. That would be switched. Yeah, so 180. Yep. About the x-axis. And that's just going to have the effect of switching the signs of those. So our stress tensor due to internal torque is 0, and then positive 4.172 is 10 to the 8th, 0. And then it's symmetrical, and that's all we have. Yep. It doesn't have to be, but in this example, it was. You know, if you have a rectangular cross section, it's always, you know, since all of the sides are perpendicular to each other, then it's all pretty easy rotations. If it's circular, then it can be anything. If it's triangular, it can be, you know, yeah, there's a big range of things it could be. Okay, so let's just get this final answer for the total stress tensor. So we're adding all these up. And you get 1.175 times 10 to the 8 for the x normal. Positive 4.332 times 10 to the 8 for the xy shear, and then it's symmetrical. and everything else is zeros. And then the rest is easy. Just take the, find the eigenvalues of that stress tensor, and it gives you a principal stress tensor at this point of 4.959 times 10 to the 8, 0, 0. And then the y normal stress is negative 3.784 times 10 to the 8. And then to find the maximum shear stress, it's 4.959 times 10 to the 8 minus negative 3.784 times 10 to the 8 divided by 2. And so the maximum shear stress you could have is 4.372 times 10 to the 8 pascals. If you have a very brittle material, then this would be enough to calculate whether it's going to break. Well, no one builds beams out of brittle materials, so actually calculating the yield stress or whatever would be pretty complicated in this case, but that's a start. Any questions? Yep. Okay. Okay. Okay, so let's say we have this. And let's say that we're looking at this. This is the point where we want to calculate it. So the capital coordinate system is always an outward-facing normal. Okay, so you can think of it as like that. We don't care about where the origin is. We always want the coordinate system with the y-axis up and the z-axis to the left. Now you just have to figure out the rotation to go from the capital to the... Oh. It should be easy to just add it in at the end. Once you add them together, it's ruined for good. Yeah, that's right. Yes. And when is the test? This Friday. Okay. Yeah. That's good to know. What? Stresses and beams. So this stuff. And that's good because we haven't covered anything after this.